Suspended in the quiet vacuum of space, a pale sphere of cratered rock exerts an invisible, rhythmic pull on our oceans and our imaginations. For millennia, humanity has charted its phases and navigated by its glow, yet the very existence of our closest celestial neighbor remains one of astronomy's most profound anomalies. We look up at the lunar surface and see a constant companion, but the true story of its genesis is a violent, chaotic puzzle that scientists are still struggling to piece together. Investigating the origin of this satellite requires us to look past the serene night sky and peer into the primordial violence of the early solar system, challenging everything we thought we knew about planetary formation. Before the space age, astronomers wrestled with competing, deeply flawed models to explain this orbital partnership. In the late 19th century, researchers proposed the fission hypothesis, suggesting that a rapidly spinning, molten early Earth simply flung a massive blob of magma from its equator into orbit. This idea imagined the Pacific Ocean basin as the physical scar left behind by this dramatic separation. However, physicists eventually calculated that the rotational speed required to tear a planet apart would completely defy the laws of orbital mechanics. As the fission hypothesis faltered, other scientists argued that our planet simply captured a passing rogue asteroid, or that the two bodies coalesced side by side from the same primordial dust cloud. Yet the physics of a gravitational capture required a highly improbable, almost miraculous slowing down of the incoming body to lock it into a stable orbit. Conversely, a simultaneous formation failed to explain why the satellite's iron core is disproportionately small compared to our own heavy, iron-rich center. The evidence surrounding these early ideas was largely circumstantial, leaving a massive void in our understanding of planetary mechanics. The turning point arrived when human hands finally reached into the lunar dust and brought literal pieces of the mystery back to Earth. The Apollo missions delivered hundreds of pounds of lunar rocks into the sterile environments of terrestrial laboratories, transforming abstract theoretical physics into tangible geological investigation. Researchers meticulously dissected these alien basalts and breccias, expecting to find the signature of a completely foreign world, or perhaps primordial material untouched since the dawn of the solar system. Instead, they uncovered a startling chemical relationship that fundamentally altered the trajectory of planetary science. The returned samples revealed a composition eerily similar to our own planet's rocky mantle, yet conspicuously stripped of volatile elements like water, potassium, and zinc. This unique chemical profile suggested that the lunar material had been subjected to unimaginable vaporizing heat before coalescing in the cold vacuum of space. The data pointed directly away from a gentle simultaneous birth and toward a catastrophic, high-energy event. To account for this baked, Earth-like chemistry, the scientific community coalesced around a radical new framework known as the giant impact theory. This model proposed that roughly 4.5 billion years ago, a Mars-sized protoplanet named Theia was on a direct collision course with early Earth. According to the hypothesis, this rogue world struck our nascent planet with a glancing, devastating blow, liquefying the crusts of both bodies and violently ejecting millions of tons of molten debris into a chaotic orbit. Over centuries, this superheated ring of pulverized rock and magma began to cool and clump together through the relentless pull of gravity. The heavier iron from Theia's core supposedly sank and merged with our own planet's center, while the lighter, silicon-rich mantle material formed the glowing, molten sphere that would eventually harden into the moon. It was a terrifyingly violent ballet of planetary destruction and creation, playing out over millions of years. For decades, this elegant narrative stood as the undisputed champion of planetary science. It neatly explained the satellite's mass, its lack of a substantial iron core, and the scorched nature of the Apollo samples. The shadow of that ancient collision seemed to settle the debate, providing a tidy conclusion to one of humanity's oldest astronomical questions. The giant impact became textbook orthodoxy, a settled fact in the minds of many who studied the cosmos. But the march of technological progress rarely leaves established theories unchallenged. As mass spectrometry advanced into the 21st century, geochemists developed the ability to measure atomic structures with unprecedented, almost unimaginable precision. They began re-examining the Apollo archives, searching for the distinct alien chemical signature that Theia surely must have left behind in the lunar crust. They were looking for the microscopic ghost of the impactor. What they found triggered an immediate crisis in the astrophysics community. Every planetary body in our solar system possesses a unique isotopic fingerprint, a specific ratio of oxygen, titanium, and tungsten isotopes that acts as a definitive birth certificate indicating where in the solar nebula it formed. Mars has a distinct fingerprint, meteorites have their own, and Earth has a highly specific signature. If a foreign protoplanet had truly smashed into our world, the resulting orbital debris should represent a mixture of both bodies, carrying a distinct hybrid isotopic signature. Yet, the advanced laboratory analyses revealed a baffling impossibility. The isotopic fingerprint of the lunar rocks is not a hybrid. It is virtually identical to the isotopic signature of Earth. Down to the parts per million, the oxygen isotope ratios match perfectly, suggesting the two bodies were forged from the exact same batch of primordial material. The alien ghost of Theia was entirely missing from the chemical record, throwing the entire foundational model into disarray. This glaring contradiction forced researchers to confront a deeply uncomfortable reality about their most cherished model. If the giant impact theory was correct in its classical form, the physics of the collision dictated that the resulting satellite should be made mostly of the impactor, not the target. Computer simulations repeatedly showed that a glancing blow would leave the Moon composed of about 70% Theia and 30% Earth. To reconcile the identical isotopic fingerprints with the mechanics of a massive collision, astrophysicists had to push their supercomputers to the absolute limits. One radical new framework suggests the impact was far more violent and direct than a mere glancing blow. In this updated scenario, the collision completely pulverized both early Earth and the incoming protoplanet, briefly creating a synestia, a rapidly spinning donut-shaped mass of vaporized rock and metal. Within this superheated, swirling cloud, the materials of both worlds thoroughly mixed and homogenized before cooling and condensing into two distinct bodies, perfectly explaining their shared chemical DNA. Another compelling model explores the possibility of a much faster spinning early Earth. If our young planet was rotating at an incredible speed, with a day lasting only a few hours, a smaller impact could have ejected a massive amount of purely terrestrial material from the bulging equator. In this scenario, the impactor serves merely as the trigger, launching Earth's own mantle into orbit to form the satellite, thereby preserving the identical isotopic fingerprint without requiring a complete vaporization of the planet. Other researchers approach the anomaly by questioning the massive scale of the singular impactor itself. They propose a multiple impact hypothesis, suggesting that our young planet was subjected to a relentless bombardment by a series of smaller bodies over millions of years. Each successive strike would have ejected a ring of terrestrial debris into space, forming miniature moons that eventually migrated outward and merged. This gradual accumulation would build the final satellite almost entirely out of our own planet's native mantle, effectively diluting any foreign isotopic signatures. These competing models highlight a profound shift in how we understand planetary formation. The investigation is no longer just about identifying a single cataclysmic event, but rather untangling a complex, dynamic sequence of cosmic violence that dictated the habitability of our world. The very forces that threatened to obliterate our nascent home were the same forces that stabilized its axial tilt, regulated its climate, and ultimately created the conditions necessary for life to emerge. The scientific debate remains intensely active, driven by the knowledge that the current evidence surrounding the event is fundamentally incomplete. We have only scratched the surface of the lunar crust, sampling a tiny fraction of its diverse geological terrain. To truly resolve the paradox of the missing impactor, scientists are looking toward the next generation of lunar exploration, hoping to retrieve pristine samples from the satellite's deep mantle, shielded from billions of years of meteorite impacts and solar radiation. Our constant companion in the night sky is far more than a silent observer of human history. It is a frozen archive of our planet's most violent epoch. By challenging established theories and relentlessly pursuing the microscopic truths hidden within ancient rocks, we are slowly bringing the chaotic birth of the Earth-Moon system into focus. The investigation continues, reminding us that the deepest mysteries of the cosmos are often found right in our own celestial backyard, waiting for us to ask the right questions.